Alright, so continue on with rational functions. Here we have one that we would probably need to use long division in order to do. So you can notice that there are two terms in the denominator, which means that it's not going to be as simple as just splitting it into different terms and then dividing off. We can't really do that very easily. So I'll quickly do the long division and we'll just see what it looks like. So I'll put the x squared minus 1 there. We've got our 4x squared take 4x plus 1. I do also recognise that the 4x squared take 4x plus 1 does factorise nicely. It's 2x minus 1 all squared, but that's not really going to be helpful for us. So how many of these go into this? It's going to be 4 first. That gives us 4x squared minus 4, which gets subtracted. The 4x squareds cancel out, leaves us with negative 4x, and then we've got 1 minus negative 4, which is plus 5. So that's our remainder. I'm not going to take this any further. However, I do need to be careful when I write the remainder because it's going to be minus 4x, and I need to have another minus here for the 5 because this one here, when it goes with this one, is going to turn into a plus. That's over x squared minus 1. So that's just a different form to write this in. 4 minus 4x take 5 on x squared take 1. Okay. So the next thing is that we can determine that the vertical asymptotes of this are going to be at plus or minus 1. And that's because I could factorise that denominator into x plus 1, x take 1. So vertical asymptotes at x equals plus or minus 1. We can also figure out the horizontal asymptote, or like any other asymptotes if they exist here. So let's do when x approaches infinity. And I'm going to use this form of the equation here. So when we do that, now you can see that I'd have to be putting infinity in for the x value in the numerator, and I'd also have to put it into the denominator for the x value there. But when we have 4x minus 5 over x squared minus 1, the x squared is going to approach infinity more rapidly than what the x will. Okay, so we talk about like x squared as being a kind of dominant function over an x. And so because of that, the denominator approaches infinity faster, which means that the fraction approaches 0. So I can say that 4x take 5 on x squared take 1 approaches 0, and so f of x then will approach just the value of 4, because we had 4 minus that thing of basically 0 here. Okay. So because f of x is approaching 4, that means that our asymptote will be y equals 4. It's approaching f of x being 4, so y is 4. We could also consider negative infinity, but you would see the exact same behavior again, so I'm not going to waste time by kind of showing that here. So then we probably need to go and calculate our stationary points. It'd be interesting to see how that goes. So f dash x is going to be, now we're going to have to use the quotient rule there, and I might actually use this second form here again just because it's going to be nicer. So when we differentiate the 4, it's just going to go, and then we're going to have, now I'll just keep that negative out the front, and then I'm just going to deal with this whole thing. So quotient rule is v du dx. So v was x squared minus 1 times du dx is just 4 minus u dv dx. 4x take 5 times 2x all over v squared, which is x squared minus 1 squared. Now that's not particularly nice. So, expanding the numerator, we get, I'll just keep that negative out the front. So 4x squared take 4 minus 8x squared, and then plus 10x all over x squared take 1 squared. We don't need to worry about expanding out that denominator. So 4x squared take 8x squared is negative 4x squared. I'm going to bring the negative into it now, so that's going to make it positive 4x squared. We've got a plus 10x becomes negative 10x, and then we've got a minus 4 which becomes plus 4 all over x squared take 1 squared. So for stationary points, let f dash x equal 0. That means 0 equals... Now, I'm going to just make this a little bit nicer. I can just say that in order for this fraction to equal 0, that's only going to happen if the numerator equals 0. You could also think of it as like multiplying by the denominator to cancel it out, but this will just be the quicker way to do it. So I can divide everything by 2 at least. So this should factorize fairly nicely into 0 equals 2x and x, and I think it's going to be a minus 2 there and a minus 1 there, which means that x must equal half or x must equal 2. So we have 2 stationary points. Let's go and get the second derivative there. Now, I'm not particularly keen to do that by hand. It's just going to be too nasty. So I'm thinking we'll do some calculator work. So bring up the keyboard, go into Math 2, and I'm just going to go the second derivative. I'll go back to the original equation. (4x squared minus 4x plus 1 over x squared minus 1, and we get that nightmare. Great. So, firstly I'm going to see if this graph has any points of inflection, so that if it does I'll know where they are. So I'm just going to solve that equal to 0. Better make sure I highlight the whole thing. Interactive equation and then solve. Okay, so we have a point of inflection at 2.85. Does it have a nice exact value? No, it does not. Okay, I'm thinking we just keep it in decimal for this one. So 2.85, and what else can we do? We can check the nature of the stationary points. So we knew that we had stationary points when x was equal to half and 2. So I'm just going to go, given x equals half, gives me a negative value. So that means that this had negative concavity. Therefore it's a maximum. And likewise when x equals 2, so I'll just change that to a 2, we have a positive value. So this has positive concavity, meaning it is a minimum point. And we know that there's a point of inflection at x equals, well, approximately equal to 2.85, wasn't it? think that's probably enough information for us. Yeah, all right. So sketching it out. We said that there were asymptotes at x equals plus or minus 1. So here's -1, here's +1. Draw those asymptotes and make sure to label them. Something we're going to do better than our last one, we're going to label our axes as well. We know that there is a horizontal asymptote at y equals 4. I'll just put that there. Make sure to label it. And then we know that there is a minimum point at x equals 2. So if that's x equals 2 there, it's going to have some sort of minimum point. I'm assuming that's going to be like here somewhere. Although that's probably not a good assumption to make, so let's just leave that for now. We also know that there is a maximum point at x equals half. Oh, I need to go and find these y values. So I'm just going to take my original equation, this part here, and then given x equals half, gave a value of 0. And then also given that x, oh sorry, I'll actually summarize that here. So we've got the point half 0, and we've also got the point when x equals 2. That gives us 3. Okay, so the point 2, 3, it's actually below the asymptote there, and that's a minimum point. And then also the point half 0 is going to be right there, and that was a maximum. There was also a point of inflection at 2.85. So that's going to be, well, that's 3 there, so the point of inflection will be out here somewhere. Probably below the asymptote, I would assume. Alright, so let's just fix that up and put that, here somewhere. So what's going to happen then is we know we've got this maximum point up here, so I'm going to make sure that the graph goes like that. We have this minimum turning point here. Now this one's a bit of an interesting one, because what that means is that the graph actually comes down from here. It's going to reach this minimum, and then it's going to have a point of inflection there and start to flatten out as it goes along the asymptote. So that's a bit strange. Now it does kind of break the idea that the asymptote is a line that the curve approaches. It is approaching it as we go towards infinity, it's just that it can also cross through it in this instance. The last part is to see what happens out this other side, which you could do by subbing a value in, but I suspect that it's going to go something like this. And we'll leave it there. I'll see you again in the next one.